we are discussing the derivative of logarithmic functions and derivatives of inverse trig functions. So let's first see log functions. We start with the natural log Ln. So derivative of a natural log function Ln x is 1 over x. Very simple formula. A lot of time we see more general logarithmic form in which the part inside the log is not simply variable x. Instead, it's some function. In this case, basically, we would apply chain rule to differentiate. So the log would be what we consider as an outer function. F is inner. So when we differentiate the outer log, according to this basic, it's 1 over. So we would have 1 over f. And then, of course, f of g is the inner, so we differentiate the inner function in the path. So with the chain rule, we can find the derivative log of some expression as this. And log is very common, important. So we just forget about the chain rule. We just call this result as logarithmic rule. All right, so this is basically the new formulas. This is basic, this is more general. Of course, we can easily derive the basic one from the general one, because if we put the x here, for f, it would be x here, 1 over x, and x prime would be 1, so it would be here, right? So in other words, this is the more useful. It's good to know how we come up with this, right? So it's simple enough, so we remember both. In addition to those two formulas we are discussing in this video, I want to point out there's a more general logarithmic sometimes when we run into too. So by general log, we mean the base is some general number, b, positive b. While in natural log, there's a base too. In natural log, the base is e. All right. So let me just write it down. By log Ln, we mean log to base e. So, well, when the base is some number other than simply e, we use b. Now, what's the derivative of a general log? It's 1 over log b times 1 over x. So we have a formula here too. And we also have a composite form of a general log, meaning the base is general number, the expression inside log is some function. Then again, we could use chain rule to find the derivative of this expression as this. Now, we don't usually discuss general log because if you do have a general log, there's a change-based formula in algebra that's going to turn this into natural log. And this is why you see the log b in general log. The differentiation formula, you see the log b in the bottom. It's because of this. So with this change-based formula, we don't really need to spend much time talking about general log. can be easily turned to just natural log with some extra stuff on the bottom. All right, so let's just focus on the natural log. Okay, let's see some examples. Now, before we get to examples, just pay attention to the formula itself. Make sure you see exactly what it says. The basic one is simple. If you have just x here, it's 1 over x. Now, the general one, when you have an expression f inside log, you can have 1 over f prime, right? That's what the formula shows. Remember, it's 1 over f, this part only on the bottom. Okay, it's not 1 over the whole log. There's no more log in the denominator, okay? Just f. All right, now we can see examples. Okay, first we're going to see the derivative of x squared times log. So obviously there's log involved. But still, we approach each and every differential problem in the same way. That is, to try to recognize the kind of function, the structure of the function, to apply the correct rule. And then down the road, of course, we're going to apply the new formula, derivative log formula, somewhere when the time comes. But anyway, so overall, the function we have here is a product. Basically, we're going to apply product rule. Okay, apply product rule later on and do whatever we have to. So let's start to differentiate. What happened? All right, anyway, let's start to differentiate. So y prime equal to product rule. So we're going to differentiate. Let me again set it up first, just so you see clearly the product rule we are applying. Right? F prime times g plus f times g prime. And then continue. You have 2x, that's a derivative of x squared. And here prime of log, that's a new thing. Well, as we know, derivative of log is 1 over x. So it's just 1 over x. And we can simplify this a little bit. X squared 1 over x, cross out x, you get just one copy of x left. All right, so it's a function involving log, and still we got to follow the standard procedure. It's to know the structure, so we know the right rule to apply. When we apply rule, take time to make sure it's applied correctly, and then apply whatever formula we have to finish up the problem. Next, let's see derivative of this function. Well, first of all, make sure you are not confused. Okay, this is a log structure. It is actually composite, like a sine inside log. Do not think this is a product. It's not a product. Okay, it's not like Rn times. It's not. Okay. All right. So it's a pretty straightforward problem. It's a log of something. So we had a formula. So log of something. The answer is 1 over that structure f inside log, right? 1 over f times f prime, just that. So let me actually copy the formula here. So it's a log of f will be 1 over f prime, and in this case this is like f. So pretty straightforward, like I said. So y prime equal to, so again let's set up the formula. According to the formula, it's going to be 1 over sine is like f, times sine prime. This is just to show that we are applying the logarithmic rule here clearly. No rush. No square. Square. All right, so then just finish up. That's a derivative sign. It's cosine. That'd be an answer. You can simplify it in trig. Cosine over sine is cotangent. You can have that. All right. So this is a more general log. It's not simply just log of x. It's log of something. Just make sure when you apply the logarithmic rule, you have 1 over f only. Like here in the example, it's 1 over sine only here in the denominator. Now, another time, the logarithmic can be complicated. The logarithmic structure can be complicated. It helps to use some properties of log to simplify first. There are 3 properties in particular that we use to simplify some complicated log. Specifically, when you have a product inside log, multiplication of 2 things or more, or even division or power. And so each case we can kind of split it. We can split the product into a sum, log of a fraction into difference of 2 simpler log. Now again, pay attention to the formula. It's a mathematics formula we use everywhere, and so obviously it's important to make sure we apply the formula correctly. Okay, and for example, like this formula is the correct one, but then if you're not careful, you could get confused. Like sometimes when people get like a log A times log B, they somehow just confuse this with log of A times B. They just say that there's a multiplication, there's log, and then just not paying much attention to the details. They again, the mistake would be with this somehow turn to a sum. That'd be wrong, right? Remember, the multiplication is inside log. The division is inside log. Power is inside log. So those type of log can be simplified. Let's see example. Okay, so we have clearly a very scary looking log. Y equal to log of product of things, right? The reason we don't want to go ahead and just differentiate in a traditional way, meaning applying the general formula, like here, they say, hey, have something inside log, right? So let's do 1 over that times that prime. We don't want to do that. because it's just so complicated. The F here is so complicated. If we just go ahead, it would be like 1 over this, right? F times this monster prime. And that's product, that's just so complicated. Okay, so we're not going to do that. We're going to instead try to apply properties of log to simplify it first. And you'll see some algebra. Once it's simplified, the differentiation is going to be extremely simple. So how do we simplify it? Well, so this is the algebraic simplification. It's not differentiation, so we're going to just continue with the equal sign. The log property here says if you have a product a times b inside log, you can break it as log a plus log b. That's what we're going to do. So this is like a, this is like a b. So we're going to have a log a plus log b. More terms, but each is much simpler than the original one. As a matter of fact, we can simplify more because second log clearly is a power. Power 3, third power here, can be moved to the front because of this property here. The power r can be moved to the front of log, right? So this power can be moved to the front. And cubic root is a power 2. Cubic root basically is 1/3 power. Cubic root of anything is 1/3 power. So with this third property of log, we can move 1/3 to the front. At the same time, move the 3 down to the front. Okay, again, I want you to know this guy is the same as x minus 1 to 1/3 power. All right, that's why we can move the 1/3 to the front. Okay, so as far as the simplification is concerned, we're done, and it's very simple to differentiate already. So let's differentiate. We're differentiating, so we start a new line. So y prime equal to. Now you see 1/3 is a constant, and the log, this time the log, is much simpler than the original one. So it's simply 1 over f. In this log, x minus 1 is like f. 1 over f times f prime. The second one similarly is 3, copy down, 1 over f prime. And we have 1. We have a derivative of this is pretty simple, negative 8x. Well, you can see the differentiation is so simple. If you don't simplify like this, if you don't simplify the structure like this before differentiating, the differentiation would be very complicated. Let's see one more example concerning the use of property of the log. All right, so we have this time log of a fraction, right? A very scary fraction inside log. Of course, nobody wants to use brute force, say 1 over that kind of thing right away. It's much better to break it off first. So how do we do that? Well, it's a fraction, so it's a log a over b equal to log a minus log b. I'm going to use this property. So log the a is from the top minus log b from the bottom. So you see the logs already look simpler. We can do better. We can simplify further. The first one basically is log of product. It's still more complicated, but we use log a times b formula again as log a plus log b to break it. So as a log a, the first one, plus log b, the second one. This log in the back is already simple enough, so we're not going to simplify it any further. As a matter of fact, the middle one can be simplified more, so let's just do that. Remember radical? Square root. Square root is like a half power. So we can move the power to the front. Just like how we did the cubic root. Here, cubic root is a third power, so we move 1/3 to the front. Similarly, square root is a half power, so we move half to the front. Now, we're ready to differentiate. So there are 3 to differentiate. Now, each is extremely simple. So y prime equal to 1 over f. F prime, I'm writing down the f prime result right away because it's very simple, x squared plus 1. We've done simple differentiation like this many times. And similarly, the second one, copy down the constant 1/2, the 1 over f prime. The last one, 1 over f prime. Derivative of 1 minus 3x. It's just that when you differentiate that. All right, again, see with very complicated logarithm. So key is you start with the log, and also inside log either you have product or you have a quotient or both. This kind of structure can be simplified greatly using these properties. Once it's simplified, differentiation of each log involved will be very trivial. Okay, so next we're going to see what we mean by logarithmic differentiation approach. It's still involved log. The idea is we have we start with some complicated function without the log, like this. Traditionally, we would go ahead and apply, for example, product rule, right? But it's going to be complicated because with the product rule later on, you're going to use chain rule here for that guy, chain rule here for this part, right? Complicated. We're not going to do it that way. There's a new way to do it. That is to try to take advantage of property of log. From the last 2 examples, we see with with the product with the fractions and log, well, the product can be split, right? So we can do take log on both sides. You'll see this is how we do it. Most of the time, there's no log to start out, and that's why we actually take log. If there's already log, chances are, look back, if there's already a log, chances are we could go ahead just apply property to simplify. There's already a log in front, right? So this is a new technique, logarithmic differentiation approach applies when there's actually no log to start with. Okay, so we actually take log just to say, hey, if you don't have log, we're going to put a log there. We're going to put log there so that we can apply properties log to simplify the complicated right hand side. So from here, the right side is like the last two examples. We'll break it into two parts, right? And continue to simplify. Oh, 3, this is a 3, so bring 3 to the front. And here is a 2 to the front, power. Just like in the last two examples. So the left side is log y, log y. Okay. We did this just so we were able to simplify the right hand side, making it easier to differentiate. Now everything is already simplified. We differentiate on both sides. So log y is a function, so it's chain rule 1 over y prime, or 1 over f prime, the same formula. The right side, of course, now it's much easier to differentiate. It's a 1 over f prime is 1 over f prime is 8x. See, differentiation is much simpler because we were able to simplify it with the log. Again, this kind of problem, we didn't start out with the log already, okay? In the original expression, there's no log here. That's why we just purposely take log on the left side, take log on the right side, just so it's possible to simplify. So finally, your y prime equal to multiply both sides by y. 2 times a is 16. So this be the answer. Let's see another example. So this time we have x squared plus 1 raised to power of sine x. This is not traditional function. There's just no formula whatsoever we can apply to find the derivative of this function. It's not power. It's not actually standard traditional exponential. It's just some structure in exponential form, but it's not exponential function. Exponential function would be a number raised to some power, which could be a function. So you see the base in this structure is a function, so it's not called exponential, so we just cannot do it. And you'll see here, if we use logarithmic differentiation method, we can do it just like before. So first we're going to take log of both sides. Okay, log y, we know what to do. It's the right hand side. With log now, we can bring sign down, power. So the property of log still applies. So in this case, reason we are applying this logarithmic differentiation approach is we want to be able to differentiate at all. The original structure, there's just no way to do it. But if we take log on both sides, we can bring the sign down. When sign is down, this is a typical standard function we'll be able to differentiate. It's just a product of a trig and a simple log. Okay, so now let's differentiate 1 over y prime. The right side is a product, don't forget. So we're going to do the product rule, derivative of the first one, derivative second one. Second one is a log, so it's simply 1 over f prime. This kind of problem, just want to remind you, people usually forget that it's a product, failing to apply product rule to try to differentiate the right side. You always end up with a product. Once you bring your power down to the front, you always have a product. If you start with this kind of exponential like, I'm not calling this as a exponential function, so I call it just exponential like. This is what I call the exponential like function. Okay, so finally the answer, we multiply both sides by y. It's 2x sine x over x squared plus 1. Okay, so this is another situation where we actually have to apply this logarithmic differentiation method. Take log of both sides, we'll be able to turn this right hand side to a product and then differentiate. All right, now let's talk about derivative of inverse trig. So there's an inverse sine, inverse cosine, so on, 6 of them. We have differentiation formulas. Respectively. All right, so on the left side, left column, we have what I call like a basic differentiation formula, meaning in each inverse trig, inside it's simply x, so like inverse sine of x. That's a derivative. That's a derivative of that guy. We do run into basic simple inverse trig, but more often than not, we run into composite structure. Just to say, instead of inverse sine of x, we see inverse sine of some function, some expression here I call the u. So I'm going to call these formulas in this right column as a u version of these formulas, meaning you see a function inside each, right? Function u inside inverse sine, function u inside inverse cosine, function u inside inverse tangent, and so on, right? Now, in this general u version, what would be the derivative? Well, what you do is to basically use this formula as a model. Replace the x by u. So this is u, this is u, here, u squared, and u prime. Now, the reason we got this is it's basically because of chain rule. All right. If you don't want to think of a chain rule, just use this as the formula, the u version of inverse sine. Okay. I'm going to show you an example. Okay, so first we see x squared times the secant x, inverse secant. It's a product, of course. We're going to apply product rule. Y prime equal to 2x, that's the derivative of x squared, times secant x plus x squared times derivative inverse secant is, according to our formula, x square root of x squared minus 1. So this is part new. Let's check our formula. Derivative of secant, inverse secant, is 1 over x square root of x squared minus 1. That's what we got here. Okay. Now, next we see fourth power of inverse sine. So, sure, there's an inverse trig involved, but we started with the composite. So fourth power is the outer, inverse sine is the inner. So we're going to apply chain rule. So y prime equal to derivative of outer power, right? Bring power down, reduce power by 1, and do not touch the inner function g, and we differentiate the g in the back. This is just to set it up, chain rule. And to finish up, inverse sine is 1 over square root of 1 minus x squared. Here. Okay. So these are, pretty straightforward problems involving trig. I mean inverse trig. There's an inverse trig involved in a product. There's an inverse trig involved in a composite. So in the product, we apply product rule. The composite, we apply chain rule. Let's see more example. So I have now inverse cosine of log. Well, first of all, don't confuse this with the product. It's not a product. This is just log inside inverse cosine. It's like the u version. So it's not simply just x here. Rather, it's a function. It's u. So we're going to use what I call the u version. Like here, inverse cosine with the log in here. So I'm going to put the log here and here. Okay. So y prime equal to, using the u version, it'd be negative 1 over square root of 1 minus log prime. So this is like u, like a u, like a u. Okay, then finish up. Log differentiated is 1/2. Okay, so this basically just shows you what you do if you have a u or function of x inside inverse trig. See one more. Here's another U version problem. So inside the inverse secant, we have this guy as U. Well, simple enough. We're going to basically plug in x squared plus x in x in the basic version. In the basic version, we have x, have x, have x. So in these three places, we're going to have the u there. X squared plus 1 is u. So according to our formula, it's going to be 1 over x squared plus 1 square root of x squared plus 1 square minus 1. The back, the x squared plus 1 prime. Again, x squared plus 1 is like the u version. And finish of the work. All right, we're going to stop here.